Yeah, I'm Caleb Gross, and today I'm going to be talking to you about exploiting insecure deserialization in Telerik UI. As a bit of background about me, I'm a prior U.S. Air Force officer where I served as an offensive cyber operations lead, and now I work on Bishop Fox's CAST team that stands for Continuous Attack Surface Testing, where we track and test our customers' external internet-facing assets on a continuous basis. And as a member of that team, I'm focused primarily on end-day vulnerability research. So if the CVE surfaces with no corresponding proof of exploit code, I'll go and pull down the software, reverse engineer it, patch diff, and hopefully get a working exploit that we'll then use to test our customers. You can find me on the tweeters at an operator. I'm giving this talk because I come from more of a binary network analysis background, and about 6 months ago, I began testing this bug in a .NET application involving insecure deserialization, and I came across a lot of new concepts and terminology that I wanted to package together and deliver for new folks who want to test this kind of bug without having to go through so much of the effort of learning like I had to do. And I initially wrote a blog post, but now I'm giving this talk in order to talk more about deserialization issues and some tricks I picked up for testing ASP.NET applications along the way. The way we're going to break this down is first I'm going to demonstrate a vulnerability in action. We're going to get a shell on Telerik UI for ASP.NET AJAX, and then I'm going to break down the CVEs that are at work behind the scenes in that demo. We'll walk through an overview of terminology that you'll need in order to understand the nature of this vulnerability. And following that, we'll use what we learned to develop an exploit that will then apply to Telerik UI. And finally, we'll walk through some things that you might come across while testing an ASP.NET application in real life, especially in the context of testing this bug. They're the things we'll talk about you can extrapolate to testing ASP.NET apps in general. Let's get to the demo. And before I show you how the exploit works, I want to share a quote that I heard from Halvar Flake recently at OffensiveCon. He said, "Exploits are the closest thing to magic spells that we experience in the real world. You construct the right incantation and gain remote control over the device." I thought that really captured what's been so fun for me about learning to test insecure deserialization vulnerabilities. You can get a shell like magic, like I'm about to show you. Now here, what you see on the left-hand side is a vulnerable instance of Telerik UI for ASP.NET AJAX, and that's going to represent our remote target. On the right side, I have a couple local windows that are going to constitute our local attack server. And now that I've mentioned ASP.NET a couple times, that's just a web framework that's built on the .NET framework. So Telerik UI for ASP.NET AJAX is a popular UI suite of components for ASP.NET applications. And it provides a lot of useful functionality, including the ability to upload files asynchronously, which I'll show you here. So this is the normal way the software works. You can, say, select an image and upload it to the application and attach it, say, to like a form to be sent via email. Now today, instead of uploading a benign image, we're instead going to upload a payload that, when loaded into the application, is going to give us a remote shell. It's going to call back to a server that we control and give us interactive control over the server. And in order to verify that this thing is vulnerable to this exploit, we're first going to compile a payload that causes the application to sleep for 10 seconds. And this is going to cause a delay in the HTTP response time, which will give us an indicator that this thing is processing our code, and we can get remote code execution on it. So there's the source that I'm going to compile. Now let's compile the payload. And while it compiles in the bottom right corner, I want to direct your attention to the bottom left, where I've got a terminal window that's going to show us exactly when our payload gets uploaded to the server. And that's just a benefit that we have just by doing this demo like this. Now that it's done compiling, let's send our payload over to the server. Okay, you can see that it uploaded successfully. If we look in the bottom left, we can see our DLL got uploaded to the server. And right now it's being loaded into the application and we're waiting for a response. And just like we expected, it took about 10 seconds, which is a really good indicator that this thing is going to give us a reverse shell if we upload a slightly different payload. So let's instead compile a payload that instead of causing the application to sleep, is going to initiate a reverse shell TCP connection back to a server that we control. And we're compiling the payload here. We also need to start a netcat listener in order to receive the incoming TCP connection that's being initiated by the remote server. So here we are starting a netcat listener. And now that that's good to go, let's send our payload. And it's going to happen really quick. But there you can see the payload got sent over in the bottom left. Our DLL made it over to the remote server, and we have an interactive shell. And at this point, we control this server according to whatever privilege levels the web server process was running as. In this case, it's running as the user tester, because that's what I started the web server as. And if we want to, we can pop a calculator. We can even kill the Chrome process that's running. Now, this should demonstrate the critical nature of this vulnerability. You can get remote code execution and even get a shell. Cool. I showed you a magic trick. Let's see what's happening in that demo behind the scenes. There are two vulnerabilities at play here in Telerik UI for ASP.NET AJAX. The first one is an unrestricted file upload vulnerability that we get via weak encryption. And this is a pretty well-known vulnerability. It's well documented, but I still think it's important to mention it here. We're going to reference it a couple times in this talk, but it's a prerequisite in order for us to then be able to exploit insecure deserialization, through which we can get remote code execution. And that latter bug, the insecure deserialization bug, is the focus of today's talk. If you're a visual learner, I've got the exploit flow laid out here. We're first going to upload a DLL, a .NET mixed mode assembly, to the server, and through insecure deserialization, we're going to load that DLL into the application using Telerik UI. And finally, that's going to give us an interactive shell. I threw a couple terms at you now that you may not be familiar with, like serialization and .NET assembly. If you're wondering what all those terms mean, that's okay, because I was in the same boat when I started testing these kinds of bugs a couple months ago. And let's go ahead and start breaking down what some of those mean. We're going to take a break from talking specifically about Telerik UI and shift to talk more generally about exploiting insecure deserialization in the .NET framework. This might be a bit of a fire hose, but what we're trying to do is equip you with the basic terminology and concepts that you need to exploit the insecure deserialization bug that I just showed you. And while we won't talk about Telerik UI just yet, we'll walk through a basic example that mimics that vulnerability we just exploited, and then apply that to the real-life vuln in Telerik UI. Now, in the .NET framework, you have, say, C# code, which looks a lot like Java, if you're unfamiliar, and that C# source code is compiled to what's called CIL code, that stands for Common Intermediate Language. This is a platform-independent intermediate code it's between source code and machine code, and it executes inside of an application virtual machine called the CLR, or the Common Language Runtime. And that's a lot like Java's JVM, if you're familiar, the Java virtual machine. And what the CLR does is it provides portability, security. It prevents some common memory corruption issues like buffer overflows. And the CLR, in turn, takes that intermediate CIL code and compiles it at runtime via a just-in-time compiler into native machine code that can be executed by the operating system. And this is all happening in contrast to the normal C program you might be used to, where you have C source that's compiled by a C compiler directly into native machine code that targets the architecture of whatever platform it's supposed to run on. And now that I've illustrated both of these things, there's this concept of managed and unmanaged code that you need to understand. Managed code, like CIL that I just mentioned, runs in the CLR in a software environment inside the application virtual machine. And in contrast, unmanaged code natively runs directly on the operating system. And when I talk about a .NET assembly, this is not like x86 assembly like you might be used to hearing. Rather, this is an EXE or a DLL that contains precompiled CIL code, and it also contains a manifest that details some information like the assembly's name and version. And this is the basic unit of execution for a .NET program. And normally, if a .NET assembly only contains CIL code, if it only contains managed code that runs in the CLR, then that's known as a pure assembly. But I want to introduce a concept called a mixed mode assembly, which contains not just managed CIL code, but it also contains unmanaged native code. So a mixed mode .NET assembly contains both managed and unmanaged code inside of the same file. And I want you to hang on to that term mixed mode assembly. We're going to reference it again very shortly. Let's shift gears for a moment and talk about serialization. This is a concept you might have heard of. So in an object-oriented programming language, you may start with an object that's been instantiated in memory. It has state and it has members who have values that have been manipulated. And if a developer wants to take that object and maybe reuse it at a later time or send it somewhere else for use by a different application, they can serialize it, convert it into a data stream that can be stored in a file in a database, sent over a network, and stored in memory. And then later on, that data stream can be deserialized or converted back into an object in memory. The exact structure, the format of that data stream can look pretty different depending on the programming language you're using. The exact format, like JSON or XML or binary, that the developer's chosen to use, and also on the exact library that a developer is using too. This is a bit of it was a difficult concept for me to think about abstractly, and what I want to do for you is illustrate exactly what serialization looks like. On the left-hand side of this screen, I've defined this class called a presenter, and a presenter can have a first name, a handle, a social security number, a couple attributes, and then I'm then instantiating a presenter object and assigning it the first name, Caleb, the handle, an operator. And then finally, I'm taking that object that I instantiated and I'm serializing it first as a JSON stream, but then also as a byte stream, because I want to show you what both of those look like. Here's the JSON stream. You can see the object that I instantiated in memory, and then what it looks like when it's been serialized as JSON. And it looks pretty similar. Like you can see all of the attributes that I assigned to this object. And now here's the byte stream, and it looks a bit different. What you're looking at is a hex dump view of the byte stream that's serialized, and on the left-hand side are the raw bytes, and the right-hand side is an ASCII representation of that byte stream. And in some ways, it's similar to the JSON stream that I showed you before, but it includes this extra bit of metadata called the type of the object that it should be instantiated as, and that informs whatever deserialization program that's converting this data stream back into an object, exactly what type of object it should be instantiated as. And now I've written a program that's going to simply take a serialized JSON stream from the command line and deserialize it and reinstantiate a presenter object. So we first deserialize that stream and then cast it as a presenter object because that's the type of object that we're expecting to receive. And so now I'm passing two different JSON streams to this deserializer program that I just wrote. The first one is the same JSON stream that I showed you 2 slides ago, but I'm adding a bit of extra data here. I added a type field that tells the deserializing program that this is a presenter type. And so when I deserialize that stream, my deserializing program takes that object and prints out the presenter's handle just to verify that we successfully deserialize this thing. So everything looks good right here. Next, if you look further down on the screen, I'm passing another JSON stream to the same program, but this time I'm not passing a presenter type. I'm instead passing an assembly installer type. And instead of passing attributes like first name and handle, I'm passing a single member called a path. And that's a path to a DLL. And we would expect that because this is expecting, our deserializer program is expecting a presenter type, that it should just complain and say, hey, you passed me an assembly installer when I'm expecting a presenter, and so I'm not gonna deserialize this, but that's not what happens. Instead, you see an exception here that says, hey, I tried to load an assembly, a .NET assembly, a DLL, and I couldn't find it. And that's because it didn't exist. But I wanted to point out that, that this error tells us that it's actually trying to instantiate this assembly installer object and load a DLL into memory, which is super interesting. And let's see if we can find a way to exploit this. There's a bit of prior research that I think you ought to be aware of if you're going to start looking at insecure deserialization vulnerabilities. A few presentations I want to point out are first, marshalling pickles. This was a presentation that happened in 2015, and it got the ball rolling on a lot of conversation around attacking insecure deserialization. And some of the response to this talk was like, okay, let's stop using Java deserialization and instead try to use supposedly secure JSON libraries, which at the time were free of known RCE vectors. And a couple years later, this presentation came around called Friday the 13th JSON attacks, where these researchers showed that these JSON libraries were vulnerable as well. And in the process, they identified an attack vector in .NET for exploiting insecure deserialization that we're going to use in our exploit today. And then finally, as this relates to Telerik UI specifically, there were a couple people who did some work that was pretty instrumental in setting me up for success as I investigated this deserialization bug. First, Paul Taylor wrote an exploit for the prerequisite unrestricted file upload vulnerability, and also developed a custom payload feature for the deserialization vuln that Marcus Wolftange reported about a year ago. And this is what the scene looked like when I started investigating this vulnerability. There was Marcus's third-party security advisory for insecure deserialization in Telerik UI, and he talked a bit about it, but there wasn't any POC exploit code that showed exactly how to get arbitrary code execution. And in my role doing end-day research for Bishop Fox's CAST service, I took a closer look and was able to work out a proof of concept exploit to get remote code execution like I'm about to show you. Let's continue where we left off in our previous example. We were able to specify an arbitrary type and JSON object the program wasn't expecting. And when we specified that our program should deserialize and instantiate an assembly installer and provided a path to a DLL, that resulting object tried to load that DLL into memory. And the fact that it behaves that way means that the class assembly installer is what we call a deserialization gadget. That is, it's a class within the application's executing scope that when it's deserialized and instantiated, it has some special side effects that make it useful for an attacker. And in particular, assembly installer is what we'll call an RCE gadget because it performs some operations when setting its path member that facilitate executing arbitrary code. So now that we understand that we can load a .NET assembly into the application by specifying the path attribute, and and deserializing an assembly installer stream. Let's see what that can do for us. As documented in the Friday the 13th JSON attacks presentation, we can create and craft a mixed mode assembly. Do you remember that term? It contains managed and unmanaged code. And inside of that assembly, that DLL, we can put arbitrary code inside the DLL main function. That's the DLL's entry point, and it's going to be triggered when the assembly is loaded into memory. And note that it's located in the unmanaged section of the mixed mode assembly inside the native code section. And typically when you, if you want to create a mixed mode assembly, you can write that in C++, and it's pretty straightforward, but we're not going to do that. We're instead going to use C in order to write our unmanaged native portion of the mixed mode assembly. And that's because I've encountered situations, it's pretty rare, but there are targets that I've tested that aren't able to execute code that was compiled from C++. And that's likely because it didn't have the C++ redistributable installed, meaning it just doesn't have the software it needs to execute code that was compiled from C++. So instead, we're going to use C. And that means it's a bit less straightforward. We'll have to compile our mixed mode assembly in sort of a piecewise fashion. First, by taking some dummy, like stand-in managed code that I'm showing you here on the right-hand side. It's just a simple empty class. It doesn't do anything, but it's important that we use it because for our mixed mode assembly to be recognized as a valid .NET assembly, it needs to contain both managed and unmanaged code. So we have this empty class to constitute the managed section, and then we compile a malicious payload in C where we put our code inside the DLL main function and then link both of those together to form our mixed mode assembly. I've shown you an overview of how that compilation process works, but I wrote a script that does all that for you and takes care of creating your assembly. I just wanted to show it to you here, but I've included a link to GitHub and you can look at the full script there. Now let's see how we can get remote code execution by crafting and loading a DLL .NET assembly into memory. We'll first write our payload here on the left-hand side, and inside the DLL main function, you can see I'm just including a message box that's going to say pwn when this thing is executed. Then I pass that source code to my build script that I just mentioned, which generates a .NET mixed mode assembly DLL, and then finally, I'm taking the JSON stream and specifying that our target program deserializer should deserialize and instantiate an assembly installer object whose path is pointing to message box DLL, the payload that we just generated. And when we run that program, you see our message box pops just fine, even though you see in the background that the program is still throwing an exception and saying, hey, you passed me an assembly installer, but I was expecting to cast that as a presenter. But even though we get an exception, our code still works. This is a really important point to note here. This is because the process of this stream being deserialized and the object being instantiated, all of that happens before that resulting object is attempted to be cast as a presenter, which means we still get remote code execution, and that's really cool. You should also note the main issue here and what makes this application vulnerable is that the program is deserializing input, untrusted input directly from a user. And here I'm passing that on the command line. In a real vulnerability that you might find in an actual application, it's likely to be passed in a different way, like perhaps over the network. So I just wanted to point that out here as well. Okay, that was a lot. We talked about deserialization. We defined what a .NET mixed mode assembly is, that it contains managed and unmanaged code. And we showed how we can craft a payload and load it into a target application via an RCE gadget that'll facilitate executing our arbitrary code as long as we control the type and the object that's being deserialized. And now equipped with the understanding of those terms and concepts that I introduced and the example exploit that I showed you, let's go exploit a real-life vulnerability in Telerik UI. In the beginning of the presentation, I showed you a demo where I first uploaded a file. And when Telerik UI uploads a file, it accompanies the contents of that file with a serialized configuration object, an async upload configuration. And that configuration specifies things like where the file should be uploaded to, the allowed file extensions that you're allowed to upload, and it takes that object, the serialized object, and it encrypts both the JSON stream and the type, both of which I've explained and showed you in an example before, and it sticks them together with an ampersand in the middle and sends it over to the server. I'm showing you here the decrypted version of both the JSON object and the type string, just so you can see what those look like and to recognize that it looks similar to the presenter example that I showed you before. Here's the bit of server-side code that's receiving that that encrypted serialized async upload configuration. And what this does is it first splits it apart based on the ampersand character that I mentioned, and decrypts the object and type, and then passes them both to a deserialize function. It deserializes and instantiates the async upload configuration object, and then finally casts it, you can see on the bottom left, as an async upload configuration, because that's what it's expecting. And here's the actual function that's doing the deserializing. It looks a bit different from the very simple example that I showed you, but the core thing going on here is the same, that this JavaScript serializer is invoking its deserialize method on a type and an object, and we've been able to specify both of those values by crafting a file upload request to Telerik UI. Let's see if we can get remote code execution just like we did in the presenter example. I'm repeating and revisiting a slide here that I showed you near the beginning of this presentation, just to remind you of the exploit flow. We're first uploading a payload, our .NET Mixed Mode Assembly DLL, and then loading it into the application by using an assembly installer type, and while deserializing, and then finally getting an interactive shell. And you should recognize we're triggering the same logic twice, that server-side code I just showed you. We're first passing a normal file upload configuration like it expects to accompany our DLL that we're uploading, and then finally we're instead passing it, instead of an async upload configuration serialized object, we're passing a serialized assembly installer to use as an RCE gadget. Just like we saw in the demo, we can first cause this application to sleep. Our C payload is going to contain a DLL main function with not message box, but sleep in that function, and that's going to cause a delay in the HTTP response. And it's really useful to verify this vulnerability because there might be strong egress filtering on the network, and this may be the only way that you can see that it's blindly executing our code. And once we compile it with the build script that I showed you as well, we're going to send it over and deliver it to the target application via a Python script that I also wrote and put on GitHub. I'm not going to show the full contents of that script here. It handles a lot of the encryption and file upload nuances, as well as formatting the deserialization logic so that the target application will process it correctly. You can see here that on the bottom of the screen, the bottom right, we get a delay of 10 seconds, which indicates that this thing is processing our arbitrary code. And now, instead of causing it to pop a message box or sleep, we're going to craft a different payload that'll cause this thing to spawn a thread and launch an interactive shell and connect us to it via a reverse TCP connection. I have sort of an abbreviated payload here, but I just wanted to highlight exactly how it's working. And then once we upload that payload and load it into the application, we'll catch the reverse TCP connection with a netcat that we have listening on our AJAX server. And here's how it works. You saw it in video form, but I'll repeat it here one more time. We use that Python script after compiling our payload, and we upload the DLL with an initial request, and then following up with a second request, we specify an assembly installer object that the program should deserialize, whose path points to the DLL we just uploaded, and it uploads it into memory and calls back to us with a reverse interactive shell. And again, I want to highlight, this is all happening because we can specify an arbitrary JSON object and type to the deserialize function that's taking place on server side. This is fixed in later versions of Telerik UI. They use a whitelist to restrict the classes or types that can be deserialized with that JSON stream. So it'll allow you to deserialize and instantiate an async upload configuration object, but it's not going to let you specify assembly installer to be deserialized, and that's going to be pretty effective to mitigate this vulnerability. While developing this exploit, I mitigated a few possibilities for our exploit to deny service to the target web application. The first way I've already showed you, I threaded the DLL payload. It launches its reverse shell logic as a thread. And the reason for doing that is that it avoids blocking the web app's user interface while the reverse shell process is running. Because otherwise the application would just kind of hang and wait for our shell to exit before returning a response. And it would block legitimate users from using the web application in the meantime. But now, since it kind of backgrounds our reverse shell, we can use the application, and so can a legitimate user. And then I also renamed the uploaded assembly on disk remotely. And the reason for doing that is because Telerik UI, the way it uploads files, say you upload 2 files of the same name, one file doesn't overwrite the other, but instead the second file is appended to the first one that got uploaded. And that can form what ends up being a malformed .NET assembly and can crash the web server when it's attempted to be loaded into memory. So you should always consider when developing an exploit, what can go wrong here? Because you really don't want to cause a denial of service. At this point, we know how to exploit the vulnerability. I want to show you what it looks like to exploit it while dealing with all the nuance that a real target provides. We're going to walk through some tips and tricks that I've picked up for exploiting ASP.NET web applications in the context of testing this insecure deserialization bug. And the theme for a lot of the things I want to talk about is that you shouldn't throw an exploit expecting it to just work. We're taking functionality, say that's intended for a file upload, and we're getting remote code execution. That's a really tricky thing, and you should be prepared to tailor the attack to the specific target that you're testing. And that target can vary in terms of the specific software version that's running, the .NET framework version, the underlying architecture, egress filtering rules in the network, and other configuration differences that cause it to behave in a way that you might not expect. The very first thing that I would always recommend doing when testing any sort of application to include an ASP.NET web app is to download a local copy of the software. And you should try to look for the exact version, exact architecture, everything as compared to the target that you're testing. And once you've pulled it down, you can run it. What I like to do is use IIS Express. This is sort of a lightweight version of IIS that allows you to quickly get an ASP.NET web app up and running without fiddling with a lot of the machine-wide settings that you often have to deal with in IIS. And then once you've got this thing running on your local server, you can debug it with an open source application called dnspy. This is a .NET decompiler and debugger and my tool of choice for this task. You can attach it to your running web application and do things like examine the modules or .NET assemblies that it's loaded into memory. And you can see one of those that I've highlighted here, telerik.web.ui.dll. That's where our vulnerable code resides. You can also search for useful entry points into the application. Here, I'm searching for the function process request. And it's one that I often look for because it's sometimes the first place that a developer is going to start writing custom code to receive and process an HTTP request that you sent to the application. And therefore, it's going to be one of the first places that might receive user input that you control. You can also I took one of the process request functions and open it up in a decompiled view. In this case, what you're looking at is a third-party component called client dependency that's in charge of fetching like static resources for a web application. And it has an LF5 vulnerability that lets you read an ASP.NET application's web.config file. And normally what I do here is enter the process request function and add a breakpoint right at the beginning of that function, so that when I start testing this, this component, that the debugger will stop and pause execution as soon as it hits that function, and I can then inspect the values of like local variables that have values assigned to them, and see exactly what's going on while testing code like this. I mentioned the web config just a moment ago. This is a file that every ASP.NET application has, and you should always check to see if it's exposed to the internet. It shouldn't be, because it contains sensitive configuration information. When disclosed, can allow you to do things like attack view state deserialization. That's sort of out of the scope of this talk, but it's important to mention here because it's pretty relevant. The web.config also contains a few HTTP handlers that I've showed you here on the right-hand side. And these handlers map directly to the process request functions I showed you a moment ago. You can see there's a process request function for the async upload handler where our vulnerable code resides. And you can see the same thing highlighted down here. This telerik.web.ui.resource path is mapped to an assembly that contains that process request function. So this is a good place to look, because these HTTP handlers often expose third-party components that bypass the core ASP.NET web page model. They're in charge of like loading static resources and doing other things kind of dynamically in a lightweight way, and therefore it might not get as thoroughly tested or looked at by developers or penetration testers, and is a good place to look for vulnerable code. I'd also encourage you always to pay attention to verbose error messages like exception details and stack traces, because this can disclose like the path to the web root, which is really good to know if you want to upload a web shell. A stack trace can also show you exactly where your attack is breaking, and I've used that many times in order to say like realize that the target web server is using an older version of the .NET framework than the version that I used to compile my payload, which made it incompatible. And so I had to adjust and tweak my attack according to the target that I was testing. Another really cool thing you can do is pay attention to if you need to signature the exact version of the software you're using, you should look at the last modified date and E tags, because those can indicate when the software was released. If you're unfamiliar with an E tag, sometimes it's structured in the format of inode size timestamp. So in this case, you have a timestamp there on the right, which you can convert from hex to decimal in epoch time, and then convert that epoch time to a date string that you can read. And now I'm showing you an example here in Telerik UI. The version string is disclosed in a resource that we're requesting. And so that's really useful. But if you don't find a version string there, say all you've got is a last modified date. And in this case, it's May 3rd, 2017, if you can see that. Let's hang on to that and then take a look at Telerik's release history for the software. You can see on the exact same date, May 3rd, 2017, they released version 2017.2.503, which tells us that this target is very likely running that version. The reason that happens is because when software vendors release software, they archive it, which preserves the last modified date on disk at the time that they archived it. And then when you later on install and extract that software to your machine, that modification date is preserved when the software is installed, and then returned to you in the form of a last modified date when you request like a static resource. But say that we don't have a version string or a last modified date, you can sometimes brute force .NET assembly versions like we need to do for the prerequisite unrestricted file upload vulnerability. And while this can normally be kind of a laborious process and you have to iterate through like hundreds of different versions, I realized while testing the software that you can sometimes get away with just specifying the major version of the assembly. And in this case, that's just 2017. And you can see that as I'm uploading my payload, I'm only providing the version 2017. And the server responds with, yeah, cool, I'm running version 2017.2.503.40. And as long as there aren't any types that are conflicting with it, that'll work just fine. So keep that in your tool belt as well. Say you can't upload your payload, or maybe you can upload it, but you can't load it into memory for some reason. As a last resort, what you can do is set up a responder server, which starts a server that can receive incoming SMB connections, and issue an attack on deserialization like I've showed you with assembly installer. But instead of specifying that its path should point to a local DLL that's been uploaded to the remote server, you can point that path via UNC path back to the responder server that you've set up. And even though .NET framework has some restrictions around loading assemblies from remote locations, it often won't let you do it. It'll still go out and try to fetch it at least, even though it won't load it into memory. And what that means is it reaches out with an SMB connection, and that allows responder to dump NTLM hashes for the server that you're attacking. And I've used that a couple times when I wasn't able to actually get remote code execution on the host. I want to share a story, which is also the namesake of this presentation. At one point, I was testing an instance of Telerik UI, and I uploaded a mixed mode assembly, but strangely, I couldn't load it into memory. I couldn't really figure out what was going on, so I watched the error messages that were coming back, and I saw that it was disclosing the internal host name of the host that I was attacking, and that the host name when I uploaded a payload was different than the host name that I was seeing when I tried to load it into the application via insecure deserialization. And after a couple minutes, I realized I'm attacking 3 load balanced servers, and I had to repeatedly attempt a deserialization attack over and over in kind of a round robin fashion until I finally hit the same host that I uploaded my payload to. And that's what brought me over the finish line by paying attention to verbose error messages. Got just a couple takeaways for you. Deserialization bugs, they continue to emerge. And I think a lot of developers and pen testers still don't fully understand them. I hope that my presentation today has demonstrated that this is really worth understanding at a fundamental level and applying a thorough approach when you're testing applications that deserialize untrusted data specified by a user. At the risk of saying it too much, always watch error messages. I can recall so many times when that's finally allowed me to exploit an application that I was really having a difficult time with. And then finally, deserialization is a pretty long word. It's a bit difficult to say and even harder to write it over and over again in a presentation like this. So I think it's a great candidate to be abbreviated with the numeronym D13N, just like we abbreviate Kubernetes with KAS. So just something to think about. That's all I've got. Thank you so much for listening. You can find links to my the exploit that I wrote on GitHub, and then also the blog that I wrote about this bug a couple months ago. If you have any questions, please leave them in the Red Team Talks Discord channel, and have a great day. Thanks a lot.